Welcome to this Python maze solving program using the depth first search algorithm. Unlike the breadth first search, which explores multiple paths simultaneously, this algorithm only searches one path at a time. When it reaches a branch in a path, it marks one cell to explore later and proceeds along the other path until it comes to a dead end. It then backtracks to the marked cell and explores that path. Let me explain this in a bit more detail using a smaller maze, which I slow down quite a bit. The red square is the start position and the yellow is the end. When the program runs, it can either go up or to the right. In this instance, the program marks the cell to the right and explores the path up. Once it completes the path up, it backtracks to the marked cell and proceeds to explore the path to the right until it reaches another branch. Then once again it marks one path and routes along the other. It follows this logic until it has finished exploring the maze. Once the maze has been explored, it uses the information gathered to find the shortest route back to the start position. This is the algorithm I use to develop the Python code, so what I thought I would do is go through it step by step using this example maze. So this is the algorithm. I'll go through it in a few minutes. Obviously this is the maze, but let me bring our attention through to these four lists that I've got here. So we have a current list, and that's going to contain the current cell that we're actually in. We have a frontier list, and that's going to contain a list of all the cells that we're going to go to next. And we have a visited list, which contains a list of all the cells we've actually visited. Then we have this solution list, or dictionary as it's called in Python, because it has two elements. It has a key element and a value element. And what we're going to do, we're going to put all the frontier cells in the key element and all the current cells in the value element. And over a period of time, these numbers will grow up, and we can use this table to route back from any cell back to the start position, from any cell in the maze back to the start position. Okay, so let's get started. So if I move my cursor to the start position, and it says current cell equals start cell. So number one is our start cell. So I'm going to put 1 in the current list, and it says go to current. So I'm going to use these little red dots as markers so we know where we are in the maze. Let's move the cursor down a bit. Add current to frontier. So basically what's that saying? Add my current cell to the frontier cell list. So that's 1. And then I'm going to add the current to the visited list as well. So current cell to the visited list. Then let's move down the algorithm. Is the frontier list empty? Nope, just put something in there. Is the current cell, which is this one, to the left in the path, or has it been visited? Well, to the left of that is the end of the maze, so this statement is not satisfied, so we move down. Is the current cell right, this one here, in a path, or has it been visited? So it's in the path, so yeah, that's correct. So we can go across to here, and it says go to cell right. So let's move the cursor to there, and it says add cell to frontier. So cell 3 becomes our frontier. That's the next one we're going to visit. And it says add the information to the solution list. So our frontier list is 3, or sorry, frontier cell is 3 I should say, and our current cell is 1. Then let's move down to here. So current cell up in path and not visited, so don't forget our current cell is 1, so we're here. So up is a wall, so we can't use that. Current cell down is a wall, so we can't use that. So let's go to this next statement here, which says current cell equals the last entry in the frontier list. So the current cell in the list is 1. It's now going to become 3, and we're going to add it to our visitors list as well, so we know we've been there. And the last statement before we loop back around again is to remove the last entry in the frontier list. So we remove that 3 from the frontier list, and we route round the algorithm again. Is the frontier list empty? No, it's not. Is the cell to the left, now don't forget we're here now, is the cell to the left in a path? Well, it's in a path, but it's been visited, so we can't use that. So let's move down. Is the current cell current cell right in the path? Yes, it is. So we can move over to here. Go to cell right. So let's put a marker there. Add that to cell to the frontier list. So we add 7 to the frontier list. And last one is that information to the solution list, sorry. So our frontier cell is 7 and our current cell is 3. Let's move down again. So current cell, which is 3, can we go up? No, can't. There's a wall there. Can we go down? No, there's a wall there. So current cell equals last cell in the frontier list. So current cell now becomes a 7, and we also add that to the visitors list. And last entry before we loop back around again is to remove the last entry in the frontier list. Take out that 7. Loop back around again. Frontier list empty. No, it's not. Current cell left in path. So our current cell is 7. Left of that, it's in the path, but it's been visited, so we can't use that. Let's go down. Can we go right? No, that's in a wall. Can we go up? Yes, we can go up, because 7 is our current, so we can go up. So go to cell up. So I'm going to move and put a marker there and add that cell to the frontier list. So I'm going to add 6 to the frontier list and add that to the solution list as well. So our frontier is now 6 and our current is 7. Let's move back around here. Can the current cell go down? Well, here is our current cell is 7. Can we go down? Well, yeah, we can go down actually. So let's move across. Go to cell down. Add that cell to the frontier list. So we put an 8 in there. And add that to the solution path, to the solution list as well. So our frontier is 8 and our current cell is 7. So current cell becomes the last cell on the frontier list. So that 7 now becomes 8. And we also go to the visited list as 8. And remove the last entry from the frontier list. Back around the loop we go again. Frontier is not empty. So our current cell is 8, so we're here. So we can't go left, it's a wall. We can't go right, it's a wall. We can't go up because we've been visited, but we can go down. So let's do it across here. So we go down, mark it as down. Add that to the frontier. That's now 9. And add that to the solution list as well. So our frontier is 9 and our current cell is 8. So current cell is the last cell on the frontier list, so that becomes a 9. And we also add that to the visited list. And remove the last entry for the frontier, 9. Let's read back around again. Frontier empty, no. Current cell left in path, so our current cell is 9. We can go left. So mark it. Go to that cell. Add that cell to the frontier list, which is 4. And add it to the solution list. So our frontier is 4 and our current is 9. So 9, so can we go current cell? Current cell, yeah, we can go right as well. So let's do across here. So this is our current cell, we can go to the right. So go to cell right, add that from the frontier list, which is 10. And add it to the solution path, solution list rather I should say. So our frontier is 10 and our current cell is 9. Can we go up? No, that's already been visited. Can we go down? No, it's not in the path. So current cell is the last cell in the frontier list. So let's take that out and make that a 10. Let's add it to the visited list. Oops. And remove last entry's frontier. Remove the 10. Back around again. Frontier is not empty. Is current cell left available? So we're at 10. We can't go left because it's already been visited, but we can go right. So go to cell right, add that to the frontier, which is 11. Add that to the solution list. So frontier is 11 and the current is 10. So 10, can we go up? No, it's a wall. Can we go down? No, it's the end of the maze. So current cell becomes the last cell of the frontier list, 11. And let's put that also into the visited list as well. And remove the last entry from the frontier list. So we take out that 11. Back around again. Frontier is not empty. Our current cell is 11 here. So can we go left? No, we can't because it's visited. Can we go right? No, because it's the end of the maze. Can we go up? No, it's a wall. Can we go down? No, it's the end of the maze. So our current cell becomes the last cell of the frontier. So we take out the 11 and make it a 4. And add that to the visited list. And remove the last entry from the frontier. So take out that 4. Loop round again. Frontier list empty. Nope, 2 items still in there. So from the current cell, which is 4, can we go left? Yeah, we can go left. So let's mark it. And let's add that to the frontier list, which is now 2. And add that to the solution key. Solution list. So frontier is 2 and the current cell is 4. So from our current cell, which is 4, can we go right? No, we can't. Can we go up? No, we can't. Can we go down? No, we can't. So our current cell is the last entry in the frontier list. So that now becomes 2. And we add that to the visitors list as well, 2. And remove the last entry of the frontier. And we route back around again. Frontier list empty, no, still 2 items in there. So can we go left of our current cell? So we're 2. So here, can we go left? No, we can't. There's a wall because it's in the maze. We can't go right because it's in the visited list. We can't go up because it's a wall. And we can't go down because it's in the maze. So therefore, the last entry, the current becomes the last entry of the frontier list. So that now becomes 6. And we add that to visited. And remove the last entry from the frontier list. So we take out that 6. And we route round again. Frontier list empty? No, it's not. So from our current cell, which is 6, which is here, can we go left? No, we can't because there's a wall there. Can we go right? No, we can't because there's a wall. Can we go up? Yes, we can. So we move the marker to there. We add that to the frontier list. That's 5. And we add that to the solution list. Frontier is 5. And the current is 6. So from 6, can we go down? No, because it's been visited. So the current cell equals the last cell on the frontier list. So 6 now becomes 5. Oops. 6 now becomes 5. We add that to the visited list and remove the last entry of the frontier. So we take out that 5 and we route round again. Is the frontier list empty? No, it's 1 item still in there. So from the current list, which is 5, can we go left? No, it's a wall. Can we go right? No, that's a wall. Can we go up? That's a wall. Can we go down? No, because that's been visited. So the current cell is the last cell in the frontier list. So I take out the 5 and replace it with a 1. And I add that to the visited list. and remove the last entry from the frontier. So loop round. Is the frontier empty? Yes, it is. The program ends. So the maze has been fully explored. So let's see if the backtracking works. So let's say if I want to go from 11 back to 1, let's see if it works. So 11 takes me to 10, that is correct. 10 takes me to 9, that is correct. 9 takes me to 8, that's correct. 8 takes me to 7, that's correct. 7 takes me to 3, that's correct. And 3 takes me to 1, that's correct. So that's backtracking mode. Let's try somewhere else. Let's try from 2 to 1. So 2 takes me to 4, correct. 4 takes me to 9, correct. 9 takes me to 8, correct. 8 takes me to 7, correct. And 7 takes me to 3, and 3 takes me to 1. Let's try from 5 just to complete it. 5 takes me to 6, that's correct. 6 takes me to 7, that's correct. 7 takes me to 3, yeah, and 3 to 1. So the algorithm works. So what I'm going to do now, I'll go through the Python code and I'll show you how I've managed to adapt the code to this algorithm. So I'll just switch over to my Python screen and we'll go through it. Okay, this is the code I've written. I actually wrote it back in 2018. It was always my intention to put it onto YouTube, but I never really got around to it. Before I start, if you want to download this code, then it's available for you to download from GitHub. Download it, play around with it, do what you want with it. I have no problems with that. Okay, so I'm not going to go through it line by line. I'll just go through each block and tell you what each block does. We'll start by going to the 3 basic functions that run the program. The first one is called set up the maze, which basically just involves drawing the grid, drawing the maze itself. The next routine or next function actually searches through the maze, explores it, and the last one creates the backtrack route and gives you the final solution, like best effectively. So let's go back to the top and I'll just go through some of the key functions of the program. So first of all, these couple of imports there, as you probably guessed, I'm using Turtle graphics for the animation, so obviously you need to download the Turtle library, and also downloaded the time library because it's nice to stop or to slow the program down sometimes to see what it's actually doing, and it's good for diagnostics as well. This chunk of code here, all that's doing is just setting up the Turtle screen. Nothing really amazing about that. I'm declaring a few variables here. Right, so this next section, I've got 5 classes, one for each of the turtle colors. So I define the shape of the turtle to be square, and in this instance it's white, and that's going to define the walls of the maze. In this class here, it's going to be for the visited cells, so it's a square, a green square, and that denotes all the cells that we've actually visited. The blue square denotes all the frontier cells, and the red square denotes the start of the program, and the yellow square is the end. Now I'm using these grids, there's 4 of them actually, and these are the skeletons I'm using to actually draw the maze itself. Now they're just ASCII characters, and I got this one from downloading it from the internet. If you just search for ASCII mazes or ASCII grids, there's quite a few sites that'll have these on there, and you can just download them. You might have to tinker around with some of the actual characters to get them to match mine, or if you want, you don't have to use crosses. You could use any character you want. So that's the framework. Now then, the first function is to set up the maze, and basically what it's doing is using this framework to define the maze itself. So the first call is to declare a few variables here, and I've got a for loop and another for loop inside the first one, so I've got a nested for loop. The first one, the first for loop, iterates through all the lines of the maze, line by line by line, and the second for loop looks at each character within the line. So for instance, if I'm not on this line here, the for loop runs through, and then the second one through, and it looks through each character, one character at a time. And if it sees a plus, then it knows it's a wall, and what it does it stamps the white icon in that position on the maze. So that's a wall. If it sees just an empty character, so for instance there, lots of empty characters, then that's the path. That's part of the path. So it doesn't actually stamp anything, but it appends it to the path list. So it puts that screen location, the X and Y screen location, in the path. So we know all the coordinates of the path. If it sees an E, like for instance there, then it knows that is the end of the or the end position, and it'll stamp a yellow square on the maze and append it to the path list as well. Likewise, yes, which stands and denotes the S at the start. So it'll just stamp a red square onto the screen. This next function is the search function, which is basically where the algorithm starts, which I went through a few seconds ago. So search X and Y basically says, let's start searching the maze from the start position. We then add the X and Y position to the frontier list, and we do the same to the solution list. And then we check to see if the frontier is empty. Well, it's not, because we've just put something in there. And then we're going to assign the X and Y values to a variable called current. Now, I know in the algorithm I use current as a list, but in reality, current only ever has one value at any one time, so it doesn't really make sense to make it a list. It's easier to keep it as a variable. So in this program, current is a variable, not a list. Time.sleep, I put this statement in there because it's quite nice to slow the program down now and again to see what it's actually doing. At the moment, 0 means it will go as fast as it can. If I put a 1 in there, it will delay it by 1 second, 2 by 2 seconds, and 0.5 by half a second. Then I've got 1, 2, 3, 4 if statements, one for each position: position up, position down, position left, position right. So let's go through one of these if statements. Let's choose this one here, which is checking to see if there is a cell to the left or not. If there is a cell to the left, then I've got this variable called cell left, and I assign the X and Y positions to that variable called cell left. I then add the X and Y positions to the solution list, and I stamp a blue square on the screen. Now, blue square, if you remember, that's the frontier square, or one of the frontiers. And then I also add to the frontier the X and Y position. And that's the same for all of these other if statements. The only thing different between these two is that I'm using the variable cell up, cell left, and here it's cell down, and here it's cell right, and here it's cell up. But the actual code and the logic is identical to all of them. So let's assume we've been all the way through the up, down, left, and right, and we come to the bottom here. Now, if you remember in the algorithm that we would remove the last entry from the frontier list and assign that to the current, which is basically what this is doing. So frontier.pop removes the very last entry from the frontier list, and I'm going to assign it to the X and Y value, but these are not the same as the X and Y values that are assigned to the current variable. They're still the previous value, because the next time it goes around the loop, that's when it gets assigned these two new values here. So what I'm going to do then after that is I'm going to stamp a green square on the screen, which will overwrite the blue frontier list unless there was a branch and it checked 2 of them, so it would only overwrite 1 of them. Hope that makes sense. These two other if statements, basically as the maze gets explored, it's putting green stamps down every cell it sees. Now eventually it will come against the end stamp, the yellow stamp, and it will overwrite it. So this is basically putting it back again. So as the maze gets explored, it hits the end position, it'll put a green stamp over it, and this will basically put the yellow stamp back over the top of it, so we don't lose track of where the end is. And it's the same with the start as well. I hope that makes sense. The next function is the back route or solution path. This is the function that produces the shortest route back to the start position, and it does this using this while loop here. So as long as the X and Y values are equal to the start value, then it opens up the solution list or dictionary, as it's known in Python. It puts a yellow stamp down, it swaps the key and the value around, and loops back around again. And it keeps doing this until it gets back to the start position and this routine ends. That's about it really. There's the only other parts of the code are really just setting up the various lists, and that's it. So what I'll do now, I'll quickly just run the program one more time. So you can see it working. Start position, and the yellow square will be somewhere down here, I believe. There it is. And the green is the visited cells. The blue are the frontier cells. I'm going to finish exploring all of the cells in the maze. It will produce the shortest route back, which I guess is somewhere like this. Yeah. Okay, so that works. That's excellent. Just to prove that I'm not cheating, what I'll do now, I'll go back to the skeleton and I'll move the end position to a new location. There, I guess. Doesn't really matter. That'll do. And we'll run it again. So it should be somewhere around here now, the end position. There it is. Okay, we're exploring a maze now. So the path is actually a very simple path back, isn't it, really, to be honest? Probably not a good example, but still. I'll tell you what I could do. Let me swap the grid to make another grid. We're using grid 1, let's use grid 2, which I think is actually a shorter grid. And what I'll do, I'll slow it down somewhat so we can see how it works in a bit more detail. So let's try that. So this is a smaller grid, but I'll slow it down so you can see where the frontier cells appear. Okay, so the visited cells have been examined. When it gets to here, one cell will become green and the other cell will become blue. Okay, so that's the frontier cell. Frontier cell again. And when it gets to here, there'll be another one here, yeah, and here, yeah, and back to here, and explore all of that. Then it should come back to this one. Another frontier cell there, yeah. Another frontier cell there, back to here. And carry on exploring to then. It should come back to this one, because that's the last one in the list. And when that's popped, it'll go back to this one. Oh, actually, it might, no, when that's popped, it'll produce 2 here, won't it? Yeah, and back to here. Then it'll pop this one. And then when it's finally done that, it'll take the shortest route back, which I guess is going to be that. Yep, great. Okay, that's it. Thanks for watching. As I said previously, if you want to download the code, then please do so. There's a link in the description below to the GitHub page, where I'll have the code and also the algorithm that I showed you earlier on. So look, thanks for watching. Bye for now.